So now that we've finished with our overview of sequential programming, its concepts, its pros and cons, it's now time to start turning our attention to more of the focus of this course. Now, as you'll see, this course is really about parallel programming, but in order to get to parallel programming, it's first useful to talk about concurrent programming. So what we're going to do here is we're going to talk about some of the key concepts that are associated with concurrent programming, which is a programming model where two or more threads run simultaneously and interact by various means, including shared objects and message passing, as we'll soon see. Not surprisingly, concurrent programming is one way to help address some of the cons of sequential programming. In particular, it helps address some of the responsiveness issues we talked about if you have input coming from multiple sources and output going to multiple sinks. And in some cases, you can also use concurrent programming to be able to take better advantage of multi-core processors. So what is concurrent programming? Here's a little pithy definition just to get you started. You can read more about concurrency at the link at the bottom of the slide. But concurrent programming is a form of computing where two or more threads can run simultaneously. And we'll see in a minute that simultaneously doesn't necessarily mean they run physically in parallel, but it means that they're logically simultaneous at the very least. Well, this, of course, raises an important definitional question. What is a thread? So a thread is a unit of execution for a stream of instructions that can run concurrently on one or more processors over its lifetime. And I typically show threads as little squiggles. They look like little pieces of thread with arrows indicating some kind of instruction pointer. So that's what a thread is going to be denoted as. But the definition here is a good way to think about what a thread is. Typically, threads run in the context of something called a process. And the process is shown here as this kind of gray round angle that the threads are running inside. And a process is a unit of resource allocation and protection. So what that means is it is used to allocate and manage resources like files, memory, network connections, and so on. And it's used as a way of protecting things because the thread running in one process cannot easily or even feasibly access threads and data running in other processes. So the process boundary concept is used to protect and prevent corruption from threads and other processes. It's possible to do some sharing of data between processes, but it's very hard, and some languages make it almost impossible without additional help, Java being one of them. Now, here's a very simple code snippet that shows the creation and starting of 5 Java thread objects that are going to be running some computation concurrently across or atop 4 processor cores. The processor cores are shown here as little Apple cores. I'm running on a MacBook Pro, so of course I have to show my cores as being Apple cores, as opposed to, say, Intel cores. So the interesting thing here is that a given Java thread object doesn't have to run on the same hardware core throughout its lifecycle, but instead it can be multiplexed across multiple cores by something known as time slicing. So say one of the threads here could run on one of the cores for some period of time. When its time slice elapses, then it's preempted. It's perhaps put to sleep. Another thread gets to run on that core. And when that first thread is woken up later, when it's time to run again, it very well may be scheduled on a different core, depending, of course, on the algorithms and the behaviors that are programmed into the underlying operating system kernel and the Java thread scheduler. Interestingly enough, multiple threads can also be multiplexed over a single core processor. So in that case, you could have, in this situation, 5 threads taking turns accessing the one core. Interestingly enough, it can turn out that even that model might give you a performance boost if some of those threads are going to block on I/O. So if a thread blocks on I/O and there's other threads available to run, the operating system can kind of park that block thread off to the side, preempt it, and then let another thread start to run to continue to use the CPU. So multiple threading and concurrency can be a useful way to speed up performance, even in a single core processor. However, single core processors are becoming very rare for general purpose computing devices. So most likely today you have at least a quad core processor, if not more, on your laptop. You probably have a quad core processor on your mobile phone, and that's just par for the course. Single core processors are now becoming as rare as upside down airplane stamps were back in the day. Threads can, of course, run in isolation, but more commonly in a concurrent program, threads interact. and they interact by various means. The two predominant means are through something known as shared objects, also referred to as synchronizers, and something referred to as message passing. Shared objects, or synchronizers, can be used to ensure mutual exclusion between and coordination amongst multiple threads. And there's a lot of different types of synchronizers. We'll talk about a few of them in a moment. Multiple threads can also communicate or interact by passing messages via queues that are properly synchronized, meaning that if one thread is reading an element from the queue, another thread cannot be simultaneously accessing and adding something to the queue without proper use of synchronization primitives. That's a whole very interesting topic that we won't have time to talk much about here, but we will talk about in another course I teach called CS 254. Unlike sequential programming, different executions of a concurrent program may very well produce different orderings of instructions. So it's kind of like rolling the dice. You may get different results each time, unless, of course, you're playing with loaded dice, which will influence how the dice will roll. But we're not playing with loaded dice here. One of the ways that concurrent programming produces different orderings of instructions is by virtue of the fact that the textual order of the source code doesn't define or dictate the order of execution. So here's a very simple example where we're going to spawn 3 threads. First thread's going to run computation A, second thread's going to run computation B, third thread is going to run computation C. And after the threads start to run, those computations could actually run in pretty much any order, especially if they themselves don't have any kind of synchronization internally to provide some kind of structuring of the order in which they run. So computation B could run first, followed by C, followed by A, or A could run first, followed by C, followed by B, and so on and so forth. Another way that concurrent programs may produce different orderings of instructions is by virtue of the fact that operations are permitted to overlap in time across multiple cores. So as shown here, somewhat visually, multiple computations can execute concurrently during overlapping time periods instead of sequentially, where one operation must finish before the next starts. As you can see, these things can run in different orders and take different amounts of time to run. Probably maybe a good example of this in practice would be going to a filling station like Costco where there's multiple pumps and there's lines of cars waiting for each pump. And the way in which those cars move through the pumps are not ordered sequentially, unlike the drive-through example we talked about before for a fast food restaurant where things go linearly from 1 to 2 to 3 to 4. Instead, things can go at different rates depending on how long they take to do their job or to pump their gas. Concurrent programming is often used to offload work from one thread, for example, the user interface thread, and then have background threads that do other kinds of work. So this is very, very common in Android, very, very common in the iPhone, iOS environment, very common in things like Java FX or Java Swing and so on. There's different frameworks for writing user interfaces. And you can see here where we have an Android architecture where there's a user interface thread that's responsible for interfacing with the person who's using the device. And then there's multiple background threads that can be used to do longer running computations that very well may end up having to block. The background threads are able to block. They may block on I/O, they may block on waiting for a database, they may block on a synchronizer, all kinds of things that you may have to block on. However, the user interface thread never blocks. And in fact, in Android, if you have your user interface thread stop for any length of time to wait for something, the system will detect this after a very short period of time, like a couple seconds, for example, and raise the application not responding error or exception, indicating that your app is hanging, which is perceived as a bad thing to do. So one of the consequences of all this is if you have state that's shared between the threads, either the user interface thread and the background threads, or between the background threads or whatnot, that any state that's mutable is just a fancy word for could change at runtime, must be explicitly protected by synchronizers or shared objects to avoid concurrency hazards. There's a whole slew of concurrency hazards. In this case, a concurrency hazard that's most common is what's called a race condition, which can occur when a program depends on the sequence or the timing of its threads in order for it to operate properly. And race conditions are very, very subtle and pernicious bugs in concurrent programs. Solving the race condition problem, plus other problems like memory inconsistency and so on, and deadlock, motivate the need for various types of Java synchronizers. And these synchronizers run the gamut from coordination mechanisms, shown by the baton passing, such as Java condition objects, to barrier synchronizers, shown by the starting gate at a horse race, such as cyclic barrier or countdown latch or phaser, to atomic operations, shown by beaming with the Star Trek transporter beam, which would be things like atomic integer, atomic Boolean, atomic long, and so on. And then finally, mutual exclusion mechanisms, which are shown here by the restroom protocol in an airplane where you've got a FIFO queue of people waiting to use the restroom and one person in it at a time. That's called mutual exclusion. And an example would be the Java reentrant lock mechanism. Now, this particular course, our course here, doesn't talk much at all about synchronization. And the reason for that is the parallel programming frameworks we're going to be focusing on typically avoid the need for needing synchronization by partitioning the data in such a way where there actually is no shared mutable state that's shared between, there's no mutable state that's shared between multiple threads in the parallel execution. In concurrent programs, however, sharing is often very much par for the course, and so synchronization is important to understand. You can often use message passing mechanisms to avoid explicitly sharing state across multiple threads. Of course, you're still sharing something, but it's coming in the form of a message, which in some ways is a little bit better controlled than having access to variables that can be read or written to from multiple threads under control of a synchronizer, of course. So again, this is a bit beyond the scope of this course, but it's a fascinating topic. And I hope at some point when you're at Vanderbilt, you can take my CS 254 course on concurrent object-oriented programming to learn a lot more about how synchronization is done conceptually as well as how it's done in Java. So that's the end of our overview of concurrent programming topics. We will continue on with a little bit more about concurrency in the next couple of lectures, and then we're going to turn our attention to the focus of the course, which of course is parallel processing.